Hey guys, hope you're having a great day. Today I just want to do a quick summary of 9.1 to 9.2. I feel like we go through a lot of cool theory in these sections, and it isn't really necessary to be able to do these problems. So it's cool because I feel like as BC Calculus students we have this thirst for knowledge, right? We want to know why things work, and so we show it. And it's really cool. I love all this theory, but at the end of the day, it's like, how do I do this on the AP test really quickly? And so we just kind of want to go through a little summary of 9.1, 9.2, especially since we have a quiz coming up. So let's kind of jump in. So we started with, what is a geometric series? A geometric series, remember, is something that you multiply by the same thing every time. So it's a plus ar squared plus ar cubed forever and ever and ever. And that is the sum from n equals 0 to infinity, ar to the n minus 1. And we said, well, as long as that r value is less than 1, these terms are turning into 0, and we actually proved that that is equal to a over 1 minus r. So, for example, if we have a series that is 14 plus 2 plus, or is it minus? Let's see here, I think it was minus. So 14 minus 2, and then plus 2/7, and then minus 2/49, and we do this forever. And it says, what is the sum of this series if it goes off to infinity? Well, we know our first term is 14. Our ratio looks like is negative 1/7, because we are alternating and we're dividing by 7 every time. So the sum of this series is a, which is 14, divided by 1 minus negative 1/7, which is 14 over 8/7. Which if we multiply by 7 on the top there, that's 98/8, or if you want to simplify that, 49/4. Cool. Okay, so numbers, not bad. We knew this formula. We learned that probably back in middle school sometime, and we just add them all together, put it into the formula, that's it. So then we said, okay, well, how about if we do this with variables? So the whole point is a over 1 minus r. Why not have a or r have an x? And you guys say, well, because that makes it more complicated. Okay, maybe, but it's really still not that bad. And we kind of flipped it on its head. We said, what if we give you the fraction? So like, what if I tell you f of x is 2x over 1 plus x? And we say, okay, what is the series that represents this? Well, we can represent this by 2x. Now our r, so our first term is 2x, our r value is going to be negative x. So we'd have 2x, and then minus 2x squared, plus 2x cubed, minus 2x to the 4th, and it's going to keep going. Okay, so this series represents this function as long as our r, absolute negative x, is less than 1. So what that means is you can choose any x value you want between negative 1 and 1. Right, the negative doesn't really matter in here because it's absolute value. And if you plug it in here, it will equal this if you add it all the way off to infinity. Okay, so like 0.76. I can put 0.76 here and here and add up a bunch of these, and I'll start getting closer and closer and closer the more terms that I use. Now, the one thing that is kind of new that we haven't seen a ton is, what if we go from a series to a function? So like, what if I give you the series, let me find it here. If we look at x squared minus 2x to the 4th plus 4x to the 6th minus 8x to the 8th, and I tell you, come up with a function that represents this. So if it adds forever, what's the function that represents this? Well, we need our first term, which is x squared, and we need our r. Looks like we're multiplying by negative 2x squared every time. So the function that represents this would be x squared over 1 minus negative 2x squared, or x squared over 1 plus 2x squared. So this function, if I graph it, and I graph this guy, as long as I use enough terms, they'll start lining up. Now, where will they line up? Well, when r, in absolute value, is less than 1. Remember, this is called the radius of convergence. And the interval is going to be, if I actually solve this out, so the negative doesn't matter. So I need negative 1 less than 2x squared less than positive 1. Well, 2x squared is always going to be positive, so I don't really have to worry about the negative end. But what I do need to make sure is that I need x squared to be less than 1/2 then. And that means that x will have to be less than 1 over root 2, which some of you may know is root 2 over 2. So it's going to have to be between 0 and, between 0 and root 2 over 2. Because, oh no, I do need to worry about the negative end. What am I thinking here? Because when I square that x value, it'll have to be sure that it is greater than negative 1 over root 2. So negative root 2 over 2 less than x less than root 2 over 2 is our interval of convergence. So radius always has that absolute value, and it's like a center around the center, the radius around the center, and the interval is going to be set up as an inequality like this with two bounds, one on each side. So we can kind of look at a graph with this. The simplest one of these that we saw is just 1 over 1 minus x is equal to 1 plus x squared plus x cubed. And you may have seen this in my 9.3 video or a different video, but if we look at this on Desmos, I'll keep my little markings there, and we go over to Desmos here, and zoom out, zoom out, zoom out, zoom out. Lots, 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 lots. There we go. Okay, here we have graphed in red 1 over x, 1 over 1 minus x, excuse me. And we see in green that as we increase that number of terms, it gets better and better and better to the red function, but only between negative 1 and 1, right? Negative 1 right now is not great. There's still some error there, but the more terms I use, the better it will get. But I will never be good like at negative 2. It's only good between negative 1 and 1. That's the only spot it's good, and certainly not over here, okay? So that's kind of the idea of geometric series in a very quick nutshell. So we started from the series to the function, and if you want to try graphing these on Desmos, see if you can come up with a general term for this. I don't think it'd be too bad. It looks like it'd be from, let's do n equals, well, we can start at, let's start at 1. Right, and that's kind of one of the things you got to play with. You got to kind of figure out what's going to be easiest. So if we did x to the 2n, x to the 2n times 2 to the n minus 1, I guess it would be. So one of the disadvantages is starting at 1. I have to start 2 at n minus 1. And then we need a negative 1 to the n minus 1 or n plus 1 to start at a positive term. Probably better to do 0 here. Let's see what it would have been. So 0 to infinity would be 2 to the n. So negative 1 to the n, 2 to the n, and then x to the 2n plus 2 to make sure we're getting all even ones. And if you graph this guy, put b up top here and just make b get bigger and bigger and bigger, and graph this guy and see when they line up. It should be between negative root 2 over 2 and positive root 2 over 2. Kind of cool. All right, so moving on. That was a special type of power series. So geometric series are special types of power series. What that means is, remember, power series just is something that has x's that increase in power. So it's something plus something x squared plus something x cubed. Now some of these somethings could be 0. Right? Like in some of ours, we only have the odd terms. Some only have the even terms. Like the last one, we only had even terms, right? But this is still a power series because the x's are increasing in exponent or power. So this is the first time I think that a bunch of people got confused because I said n equals 0 to infinity, c sub n x to the n, which is c0 plus c1x plus c2x squared. And everyone was like, what the heck are those c's? And I was like, they can be whatever you want them to be. Sometimes they're geometric. Sometimes they are like a Taylor series. Sometimes they are nothing. Great example that I thought of was, what about this? 1 plus x plus 2x squared plus 3x cubed plus 5x to the 4th plus 8x to the 5th plus 13x to the 6th plus 21x to the 7th. Anyone recognize what these numbers make? 1, 1, 2, 3, 5, 8, 13, 21. These are the Fibonacci sequence. Still a power series, though. It doesn't have to be geometric, doesn't have to be a Taylor series. Anything that has increasing powers of x is going to be a power series. Now, this might not converge to anything. These numbers are getting bigger, and it's maybe when x is 0, for sure it will converge. When x is 0, right, this is going to converge to 1 every time. Doesn't matter how many terms you use, because all of them will disappear, except for that first term of 1. But the point is, for some other values, maybe like if x is small, maybe this will still converge. I don't think it will, because these numbers are getting bigger and bigger, but it's possible. But the whole idea of a power series is just that it has increasing values of powers of x, and then if you want to center it somewhere else, n equals 0 to infinity, cn times x minus a to the n. That just means you're shifting it by a unit. So it'd be c0 plus c1 x minus a plus c2 x minus a squared. So that just means that you want it to be good somewhere else, right? You want it to be good somewhere else at x equals a. When x equals a, these will all cancel out. You're just left with that first term. So, Taylor series. What is a Taylor series and what does it do? Well, the Taylor series for a function, so f of x can be approximated by f of 0. We'll start with the Maclaurin series. So Maclaurin, remember, means that it's centered at 0. So Maclaurin series means that it's centered at x equals 0. And what happens is you approximate all of the derivatives using this thing. So we have f of 0 plus f prime of 0 x plus f double prime of 0 x squared over 2 factorial plus f triple prime x, 0 x cubed over 3 factorial, etc., etc. Now, the great thing about a Maclaurin series is on the nth derivative, the exact term you want will be there. So we want to make sure that f triple prime of x is equal to, well, let's say of 0, is equal to this polynomial's third derivative. Well, let's think about what's going to happen by the time we get to the third derivative. The first derivative, this constant term will be gone, because f of 0 is a number. And then the second derivative will make this term go away, because the x will have gone on the first one. This one will be gone because the 2 came to the front, then the 1 came to the front, and the x went away, and then everything was a constant, so it went away. This is the only term that's going to matter, because I'll have 3 times 2 times 1 x cubed divided by 3 factorial. Well, that is 3 factorial, so they go away. There's no x cubed left, because I'm at the third derivative, so then I have f triple prime of 0. So the reason I chose to put that in front of x cubed is because that's exactly what I want to happen on the third derivative. So this will just have the correct derivative left as a constant, because all of the constants will cancel with the 3 factorial. The x will be gone, because that's the exact derivative I'm on, is when the x disappears, because like the derivative of 2x is 2, right? So that'll happen on the last step before each derivative. So this function, this polynomial, will correctly mimic the derivatives of f of x for as many degrees as you have out. Which is why this is so powerful, because that means that the shape of the function close to that center, so centered at 0, this will do a really nice job mimicking the function close to 0, which is why we use it. Now, if you want to center it at a instead, so at x equals a, so this is not a Maclaurin series, because Maclaurin just means it's centered at 0. So if I want it centered at x equals a, I just do, okay, f of x still, not x minus a or anything. I'm just approximating the function at a different value. So I do f of a plus f prime of a times x minus a plus f double prime of a x minus a squared over 2 factorial, and you keep adding those up together and forever and ever. So to create one of these, so this is good close to a. In fact, if you plug in a, whoops, go back a slide. So this is good close to a, because if you plug in a here, all of these will turn into 0. You'll just end up with f of a. Here, if you plug in 0, everything goes away, and you just end up with f of 0. But close to a, this is the one that you're going to want to use. This, for some functions, the top one will converge for all values. Sine x, e to the x, cosine x are 3 examples. But like for a geometric, even if you do it this way, as opposed to doing it the easy geometric way, it'll still only converge for absolute x less than 1, right? So sum n equals 0 to infinity, nth derivative of 0 times x to the n over n factorial. In this case, sum n equals 0 to infinity, nth derivative of a, where if n is 0, then that just means f of a, or f of 0 up here, x minus a to the nth power divided by n factorial. Okay? So trying to approximate functions close to a certain value, not necessarily geometric, can be anything. And that's what you need to know. So which ones do we need to know? Well, AP requires you to know 3. AP requires you to know sine x, which is x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial. It's all the odds, minus x to the 7th over 7 factorial. Hopefully you're tired of seeing this by now, and you know it. N equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. Should have that at the tip of your tongue, even the sigma notation. Cosine x is the evens. 1, don't forget the 1, minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, etc., etc. Don't know why I went that far with that one. That is sum from n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. Nifty. e to the x. E to the x is my favorite. It's an easy one. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus forever and ever. Sum from n equals 0 to infinity, x to the n over n factorial. If you know these three, you're going to be in good shape for the AP test. They also mention usually in this line that you need to know 1 over 1 minus x is 1 plus x squared plus x cubed, etc., etc. Sum from n equals 0 to infinity, x to the n. This is geometric though, right? So the geometric ones I feel like you should know. If you ever have a fraction where you've got 1 minus something in the bottom, that is like flashing lights. You're looking for geometric. You can do this by using Taylor, right? The system to come up with this Taylor polynomial is just start listing derivatives. What is f of 0? Well, in this case, it's 1. What is f prime of 0? Well, f prime of x is 1 over 1 minus x squared. So 1 minus 0 squared, which is 1. F double prime of 0. Now that 2 is going to come to the front. So I'm going to have a 2 over 1 minus 0 squared, cubed, excuse me. So that is 2. And the next one's going to have a 2 times 3, because that 3 is going to come to the front. So that's going to be 3. And you can put a factorial, because 3 times 2. The next one's going to be 4 factorial. So what happens is all of those factorials cancel out, because we have f of 0, which is 1, plus f prime of 0, which is 1 times x. So what I'm doing here is I'm building the Taylor, but showing you it's the same. The next one is going to be 2 times x squared over 2 factorial. The 2's cancel. Then we have 3 factorial x cubed over 3 factorial, because the derivative is 3 factorial. Those cancel. So we just end up with 1 plus x squared plus x cubed. But it's easier to think about this as geometric. Harder to think about in terms of the Taylor. Okay. So these are the three you really need to know. And the question is now, okay, which are nice to know? Well, we said the 1 over 1 minus x is one that you have to know just because it's geometric. Natural log of 1 plus x. This would be the antiderivative of 1 over 1 plus x, which would be the antiderivative of 1 minus x plus x squared minus x cubed forever and ever and ever, which ends up being, so this guy is x minus x squared over 2 plus x to the third over 3. Notice there are no factorials. That's important for natural log. X to the fourth over 4, and this will keep going, okay? And then tan inverse, this is a kind of a special one because it's the antiderivative of 1 over 1 plus x squared, which would be the antiderivative of 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth, etc., which ends up being x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7. All the odds, but no factorials, because that would give you sine. Okay, so nice to know, need to know, nice to know, need to know. So sine, cosine, e to the x, you must know. These guys, they're nice, but you can derive them, hopefully, if you think about them for a second or two. But often AP will kind of guide you into this part if they ask questions about these. So how do we use these building blocks? Well, all kinds of ways that you can do this. So one thing that they often ask you to do is they'll say, okay, if we give you this function, you have to be able to find it. So like if we do x sine x, okay? So x sine x would be x multiplied by the sine function. So it'd be x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, etc., etc. And we can just bring that in. So it'd be x squared minus x to the fourth over 3 factorial plus x to the sixth over 5 factorial minus, etc., etc. You come up with a sigma for that. Looks like it would be sigma from n equals sort of 0 to infinity. So now usually, so sine, remember, is sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 factorial. So now all we're going to do is we're going to add 1 to that exponent, because that's all we did was we add 1 to the exponents. So we have sine is going to be negative 1 to the n, because it's alternating. And then it's x to the 2n plus 2 divided by still 2n plus 1 factorial, because that hasn't changed on the bottom. Another one they could ask you, they could do like, all right, what's e to the 5x? Well, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So all I'm going to do is replace all these x's. So this would be 1 plus 5x plus 5x squared over 2 factorial. Now you could do this as 25, but leaving it like this is so much easier to do the general term. 5x cubed over 3 factorial, and that'll go on forever. So that would be the sum from n equals 0 to infinity, 5x to the n over n factorial. So much easier to do that way. Now that last one kind of leads into a question, and I'll use this last slide to do my last one that I wanted to do. If they give it to you the other way, so they could say what function, like what common function is represented by this series. So they might give you 1 minus x to the 4th over 2 factorial plus x to the 8th over 4 factorial minus x to the 12th over 6 factorial, and keep going like that. So when you look at something like this, you kind of have to say, okay, what are the only 3 AP requires me to know? I only have to know sine, cosine, and e to the x. Those are the only 3 that I need. So it's got to be one of those 3. Well, probably not e to the x, because e to the x doesn't alternate, right? X squared over 2 factorial, 3 over 3 factorial, right? No alternation, so probably not going to be that one, unless it was like an e to the negative x or something like that. Sine has all of the odd numbers, so I don't think it's going to be that one, but it looks like it's even numbers, so probably some kind of cosine. Now these powers are what's messed up. So what I like to do is think, okay, cosine, I know at bare bones, is 1 minus something squared over 2 factorial plus something to the 4th over 4 factorial minus something to the 6th over 6 factorial. It's all the evens. So then I say, how do I get these? Well, something squared, that something could be x squared. Ooh, cool. So then this something to the 4th, well, that could be x squared. And this could be x squared. Hey, we're on a roll. So this looks like it is cosine of x squared. And you've got your function. Okay. So sometimes it's given the function, you have to plug it in. And sometimes, like in this case, they give you the series, and you have to say, okay, how can I make this series using sine, cosine, or e to the x? And in this case, it wasn't too bad. It was just cosine of x squared, so not bad at all. So that is a very quick and dirty summary of 9.1 to 9.2. This is what your quiz is on. If you want to see more detail, Ms. Galt made some excellent screencasts. Feel free to check those out. They're on Schoology. There's also, I put one Khan Academy video on there. I'll just show you this right now. So if you go to Schoology, I got it up right here, and you go to calculus, because that is pre-calculus. Let's scroll up here. Courses, calculus, there we go. And we go to our screencast worksheets and solutions, which is where everything is posted. Chapter 9, scroll a little bit. Here we have Galt's, all of Galt's screencasts, as well as a Power Series video from Khan Academy. So watching those, definitely going to give you more info, more in depth. I probably have these collapsed into a folder now just because I haven't posted these guys online yet. But this is just kind of a summary. And then the 9.3 one, remember that there is no error, there is no 9.3 on the quiz, so don't worry about that. I love you guys, that's why I'm here. Best of luck on your quiz, and I will see you when I am back. Good luck.